Why was NaClO2 initially considered to be a material suitable only for anode applications based on its electrochemical properties? How did you at all overcome this limitation by preparing 9I.5.502 through a combination of 9IO2 and O3-NaClO2 as shown in figure 3.14a? And what advantages does this composite approach offer? In what manner does the incorporation of titanium improve the cycle stability of the material? And how does the presence of the Ni superscript 2/redox couple contribute to achieving a relatively high specific capacity? What insights can be drawn from the electrochemical performance data shown in figure 3.14b regarding the behavior of 9I.5T.502 when used as a cathode material in sodium-ion batteries? How does the material manage to retain a capacity retention rate of 75% after 300 cycles? And what mechanisms might be responsible for this level of durability? Can Davis Syrinz manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do the modifications in the material's composition and structure alter the intercalation kinetics compared to the original NaClO2, and what impact does this have on the overall battery performance? What further research is needed to optimize the balance between cycle stability and specific capacity in such composite materials, and how might these insights guide the development of next-generation electrode materials for sodium-ion batteries? How does the crystal structure of O3 type NaClO2 define the arrangement of sodium, vanadium, and oxygen atoms, and what does the designation O3 type imply for the layering and stacking sequence within the material? How are the Na ions positioned within the structure, and what kind of coordination environment do they have with the surrounding oxygen atoms? What role do the VO6 octahedra play in the overall framework of the compound, and how are these octahedra connected by edge sharing, corner sharing, or otherwise? And how does that connectivity influence the material's properties? How do the lattice parameters and unit cell dimensions of O3 type NaClO2 compare with those of similar layered oxides, such as NaFeO2? And what insights can be drawn from such comparisons regarding ionic mobility and structural stability? What is the space group of O3 type NaClO2? And how does its symmetry contribute to the physical and electrochemical behavior of the material? How does the stacking of oxygen layers in the O3 type structure affect the diffusion pathways for sodium ions? And in what ways might this impact its performance when used in battery applications? How do potential defects, such as oxygen vacancies or cation disorder in the lattice, influence the crystal structure and, subsequently, the electrochemical characteristics of NaClO2?